Hello, everyone. My name is Min-Shen Pan, and I'm here to talk about axes and scales. I work for Wolfram in the visualization team for many years now, um, and I hope you will enjoy this talk. So about this talk, I'm going to talk about scaling functions. This function has been um, in Mathematica for many versions, and we have done some work on it, and we will look at it that what we have done more in for version 13. We'll also talk about axis object, which is new in 12.3, I think, and how it is used and will be used in visualization functions. This graph that on the screen is the one that Stephen showed in his keynote. And this is, and also mentioned in Brad's session. So basically, on the left one is an unscaled version, and I will show you that. Well, so how to generate this plot is really painless, but I will show that the underlying transformation and the mechanisms of scaling functions, how it works, so that how we pack this different range of plots into a infinite domain that you can see the trend. So in the beginning of this talk, it's going to be like scaling functions 101. I will talk about how scaling functions work, meaning that a lot of people ask that why does scaling functions need scaling function and the inverse scaling function. So I hope that within this process, you can understand that why the inverse scaling function is needed. So let's just go get started. So many occasions you will want to scale a function. For example, like this x to the power of 2, you want to apply to log edit. So internally, the scaling functions is nothing but also just doing the same thing here. We just apply the log on the function. And then the y direction now is in the scaled domain, which is log. And then the ticks automatically is from also in the scaled domain, so that you can see the ticks is not what we want to see, which is we still want to see 0 to 10. So what we can do is that we can use the ticks option, and you just specify the ticks. So the syntax is that you specify where the ticks to be at and what label you want to see. In this case, those ticks from the plot above is -2, 0, 2, 4. So we could just copy that and say that we want to see them at these locations. But of course, these values now is in the correct domain, which is the original domain, but they are not nice values. So what we really want to see is to see the 10-based log ticks. So what you can do is that instead of deciding the location first and choose the labels, we can choose the label first, 0.1, 10, 100, and use the scaling functions to figure out what the locations are. Or, instead, you can just call the scaling function, say log, and then we handles this for you. And you can also see that for these simple examples, I only specify the major ticks. So you get the 0.1, 10, and 100, and nothing in between. But in the automatic ones, we have the minor ticks. So that is for the functions domain. So on the y-axis, what if that we want to scale the domain? Meaning that what if I want x direction to be in log scale? So we will need to do some variable replacement trick. So first of all, we have to scale the domain, which is 0.1 to 10. We'll scale to log 0.1 and log 10. Now the x, which has a new variable called the xx, is in the log scale. So we will have to use the inverse scale to apply on the variable. So when it's plots, when it plots, it is still plotting the correct values. Again, if you want the ticks to be correct, you will have to do the same ticks treatment here. So the scaling functions allows you to specify different scalings in different directions. So this is the syntax. The first one is the x direction, and y. The second one is the y direction. So this is how you can work on it. So that just gives us the basic idea how scaling functions works, and also gives you the idea why we need inverse scaling function, because the inverse scaling function is essential to figure out the ticks and also for the domain when we do the domain scaling. We have quite a few named scales. We have log, log 10, also log 2, and reverse, reciprocal, and we added signed log and the infinite scales. But in general use, you can just specify your own scaling function and the inverse scaling function. For example, log is equivalent to log exponential, and log 2 is equivalent to this. And the scaling functions take, like I said, you can specify in different directions. Some functions like the plot, you can specify x direction and y direction. Functions like plus 3d, you can have x, y, z. So they are all documented in each visualization function. So let's take a quick look at these named settings. For the log, the reason we have like log, log 2, and log 10 is mainly because the ticks. For the log 2, you get 2 based ticks. So you can see that they are all 2 to the power of 2, 2 to the 4th, 2 to the 6th. And for the log 10, then you get a classic log scale look. So if you have a function that goes from 1 to 100, then you get the 2 major ticks, 10 to the first and 10 to the second. And then we quickly realize that there is an issue if your range is not to 100, it's just only like half value there, then you just get a 1 major tick. But we don't, and then we saw that it would be really nice if we still have some major ticks so that you can reference your lines easier. And that is when we figure out that we can take the liberty of using the log, because no one is displaying the exponential constant as the base on the log ticks. I mean, you can, but that's not a convention. So instead of maintaining the 10-based ticks, we added some other major ticks here. So the way to read this is that in this order from 1 to 10, you get 2, 5, 10. So the next order, you get 20, 50, supposedly 100 on the top. So I hope that in between the major ticks, you have the minor ticks that will guide you where the values are. Right. And again, I really want to emphasize that the scaling functions can be applied in different directions. And we do have shorthands. When you just specify log here, this is for plot, it is automatically to be on the y direction. For different plots, these shorthands have a different settings, but mostly they are on the y direction or the z direction. The reverse is a scaling functions that is useful in some applications. And this reverse is nothing but just negative applied to the values. And then you can see the inverse scaling function and the scaling functions are the same, because the inverse of minus slot is minus slot. And what you get is a reversed look, and the ticks is also reversed. And reciprocal is 1 over x. and its inverse scaling function is also 1 over x. And you can see here, and I have to admit that the TICS is a difficult business. In this example, the TICS kind of like cramped together, and we are still constantly trying to improve how the TICS behave. But the reason we did not try to meddle too much on the TICS here is so that for the reciprocal scaling function, it is just difficult to get a general TICS scheme to work for all the functions. And we also introduced the sign log in version 13. So the reason we introduced sign log is that it is obvious, like when you apply log to the sign or to a function that has negative values, the negative values is it doesn't exist. So then you get a plot like this for example, for the sign of x, all the negative values just get clipped or dropped. But it is desired to see the negative values also in the log scale. So this is where we introduce the sign log, which is a shifted log. So here I'm trying to, I will try to explain how that works. So I have a plot here that is plotting exponential of to the x and an exponential function, both on the positive and negative values. So if ideally, if we apply log scale, well, which negative values will be dropped, but the positive values will be a straight line. That's a test case that how if our scaling function is working on the exponential function. And our sign log is the same thing. Instead of just log x, we added a +1 here. So like there is no values between 0 and 1. So every value is shifted up. And you can see here, when I applied sign log, these two lines are not exactly straight because of the shifting. But when the values are larger, they are straight lines. Right. So now if we plot the log sign, sorry, if we plot the log of sine x again, you can see the full sine of x can be scaled. And so this scaling functions also has a parameter there. This is for you to specify that where you want to emphasize the scaling function. So if I specify 0.01, and then you will see that the effect is more dramatic because closer to 0 is stretched out more. So this is a parameter for signed log. Next one is the infinite scale. This is on the domain. I mean, it's not necessary to be on the domain, but it is by default, if you have a domain specified from -infinity to infinity, or really just like if the infinity it appears in either position, then the scaling functions on the x will be automatically applied. So this is the look of the sinc x, which is sin x divided by x. So how does it work? So the function that we are using to rescale this, to do the transformation, is using rescale. So basically, rescale has a special handling on infinity. So we are trying to scale the original domain, which is -infinity to infinity, to -1 to 1. And how it looks like is here. So this is f of x -1, and then this is a function here. To find its inverse function, we can just use system inverse function. Then this is our inverse function. So to plot this transformation function, you can see in this plot. So X direction is the original domain. Y direction is the transformed domain. You can see how it tapers quickly to 1 and -1. So, but this is just one of like infinite transformation function. You can like change this transformation function so that it tapers much slower. And also there are other functions like this polynomial function that provides similar curve, like tanh or arrow function or logistic sigmoid. And we provide, because that we understand that, and also the fact that you can stretch this transformation function differently, just like sine log, we introduced a parameter for infinite scale. So the syntax is like this. So well, if you don't specify scaling functions at all and infinity appears in the domain, it will just apply it with the default. But if you do want to choose a different parameter, so this is what you need to do. Oops. Don't know what happened. Sorry about that. There we go. So you will have to specify an interval that you are interested in looking. So you can specify -1 to 1 in this case, and then you can see how this infinite scale stretches the region -1 to 1 much more than others. If you want to stretch from -1,000 to 1,000, I don't know why this is doing this. I'm so sorry. Then, well, so that's probably a little bit too much. Right. Right. So then you will have this infinite scale stretched much less in the origin. And the application of infinite scale automatically is finding the limit and visualize the limit on the plot. This Brett also mentioned this in his talk. For example, to find the limit of this function, we can use the system function limit when x go to infinity. So it is 1 over the exponential constant. We can just plot this function, and then you can see that at infinity, it just touch this point. And for another example, a polynomial, a rational polynomial function, the limit of this function is dictated by the coefficient ratio of the highest order element. So nothing, down the rest matters. So this limit is 3 divided by 2. So we can see this on the both end, they are the same, the limit. And you can see that when it reaches -infinity and infinity, they just touch this this limit. And I included a bonus for you to look at it, how to use scaling functions to test a function, how it closes, how close it is to a reference line. Another scale we added is date scale. So what this does is that when the functions like this line plot or this plot sees a data that contains time series, it's going to automatically apply date scale on the x-axis. So, I mean, I can just plot daily plot with this financial data, but now you can just do it with this line plot automatically. Here's an example of sunset data and sunrise data. These two lines are both time objects. Sorry, what I meant to say is that on the x coordinate, they are the dates. So in the x direction, you get the date axis. And since the y direction is also time object, I also specify the date scale on the y axis. So this is, so you can easily visualize the dates with the date scale. So you may ask that, why do we need the date scale in the this line plot when we already have the date list plot? That is true, but this is just one example in the greater scheme that we are trying to support date scale in many visualization functions, if not all. So for example, in this line plot 3D, you could have 2 time series and just plot it, and then you will have the date ticks, so that we don't need to introduce date this line plus 3D or date bubble chart or date anything plot. So the date scales will just be exploited and rolled out in all these functions that have scaling functions. So the functions with scaling functions so far are these functions. And granted that not all of them are very relevant. One trying to say is that a lot of them are in very special domain. The scaling functions are handled differently. For example, the body plot and the Nicholas plot, they have their own scaling functions named sets. So they are all mentioned in documentations. But the goal here, and hopefully in the version 13 and above, we will continuously add the automation of scaling functions in different plots. Next, I'm going to talk about axis object. So axis object is introduced into point 3. And for the detail, please see James' talk on the graphics, new features, improvements. That will be tomorrow, 11:30. So to be able to fully appreciate axis object, I have to torture you with the ticks, which is the system ticks, if you haven't used it before. So for example, we had this plot before, right? X squared and the scaling function called log. So what if I want to change the tick styles? What if I want to style them to red? Well, there wasn't a tick style options before. So you will have to actually specify your ticks first. And you have to specify the tick length, for example, this case, and you have to specify the style of it. And just imagine you have to do this for every ticks. And I'm only putting the major ticks here. The minor ticks you still have to specify. So this is quite a headache. I mean, granted, it gives you the ultimate power to control every detail in the ticks. But for the most of application and most of people, they don't really need this detail control. And this is just one of the benefits of the axis object. Now it provides all the options, so you can just individually specify what you want to change. But most importantly, ticks is strictly associated to the system axis. That means that you can only apply to the horizontal and vertical ticks, axis. For the axis object, there's a reason, this is from documentation, that we did not draw it horizontal or vertical. We draw it in an angle to indicate that this axis object can be in any shape. it's not even just in a straight line. It can be circular. So for the detail, again, see James' talk tomorrow. And here is just an example that how you can specify all different options individually. So I'm just going to try this one. And you can change the tick labels easily. You don't need to specify all other options to change the labels. And with this capability, we can now easily generate a framework for ternary plot. Ternary plot is a system that you have is a barycentric plot. So you have a point that is x, y, z. However, there are only two freedoms. So x plus y plus z has to be a fixed value. Well, anyway, so we couldn't do this before without like pulling our hairs to figure out the axis and ticks. Now with the axis object, this is very easy to do. And the visualization functions that we currently have that will eventually use the axis object includes the radial axis plot. So it is really not uncommon that the axis exists, spatial axis exists in many visualization functions. We also have the parallel axis plot where the overall plot range is something like -1 to 1, but we are scaling every line to fit into this range, and we use our customized axis to draw this many axis. Currently, it is not using axis object, but it will be. And the development of this kind of plots will be much faster. So I'm running out of time. This is just an example that how other plots are using customized ticks, and they are just everywhere. And please looking forward to these new changes in version 13. The last one, I'm going to just skip, quickly go through that scaling functions also works in the axis object. Here is a way you can specify how you want to scale the ticks. But with scaling functions going to work in the axis object, you can have your own customized plot much easier especially if you want to combine plots together. And last one example is that the infinite scale also works on axis object. So so that will conclude my talk. I'm going to try to answer a question here. So can we specify the format of the axis text without specifying the text? My colleague has answered that. So so it looks like what you're looking for is something that we have in mind, and we will work on it more. Will scaling functions being implemented for slider? That is a good question. So I'm running out of time. So we have an office hour at 2 o'clock. So please come to our office hour, and if you can, and we will answer the questions later. Thank you so much.